the floor is yours. So please go ahead. Thank you.
Thank you again, Professor Maha, for the introduction. I'm very pleased to give this presentation in this webinar. This is the second time I meet with AFRONE, so I'm happy that I can deliver this webinar. Okay, let us start. Bismillahirrahmanirrahim. The title here is Artificial Intelligence Case Studies in Dentistry. And we will take one example to focus on during this webinar, which is the image segmentation problem. I will go define the problem first. What is meant by image segmentation and what are the spectrum of segmentation tasks, such as semantic segmentations and instance segmentation. And then I will give more details, if time permits, how the model actually learns during the training loop. Okay. So the first thing, what is image segmentation? How to define your segmentation task, understand your objective and your input data, and define what is your metrics of success. Select that learning paradigm, and we'll give some examples. And set your evaluation criteria, visualize your results. Everyone knows this process because if you did research in this field, then you understand what I mean. But let us start from the very beginning. What is image segmentation and how it fits the AI in case studies in dentistry. So what is the task? We'll define two tasks. We'll define something called the semantic segmentation. I will give you an explanation what is meant by semantic segmentation and what is instance segmentation. These are the tasks. And what are the desired outputs? It depends on this depends on the task on hand. For example, you might look for some lesions in X-ray scans, or you would like to do volume calculation in CBCT volumes, but to do this volume calculation, you first need to identify the voxel that belongs to the thing that you are looking for. So segmentation is very important in both tasks. So segmentation tasks, let us give brief introduction that is not related exactly to the dentistry. Image segmentation is key topic in processing images in computer vision tasks, and we can see many applications in medical image analysis or even in other self-driving environments or robot perception and whatever. So what we can see here is that you have an X-ray at the left side, and you have some highlighted parts of this X-ray, and this might refer to some fraction or some artifact here. And the segmentation job here is to identify the pattern or the fraction that you are looking for. Also, in the middle, we can see the liver segmentation from CTs. Also, we can find this maybe some tumors in brain MRI, or maybe you can do this on ultrasound. So what is the purpose of the slide on the left part is that the segmentation task is to highlight this part and give it the same color coding, highlight this part and give it the same color coding, highlight this part and give it the same color coding, highlight this part and give it the same color coding, highlight this part and give it the same color coding, and same here. And actually, it shows us that segmentation can be applied to different modalities. For example, X-ray is different from CTs, MRIs, or ultrasound. And also, it can be done on RGB images that we can see on the right side of the slide. It is applied on this outdoor scene. Some people are walking, some cars are here, some wall, some buildings, some we have a sky and other trees, houses, and so on. So what is the task here? Also, again, to give the same color code for the same class. So and this is called the semantic segmentation task. Semantic segmentation task, it means that every pixel in the image should belong to some semantic class. And this semantic class is defined by the problem owner. So we like to look for something that is present in the image, and we'd like to identify which pixels which pixels belong to that class. So for example, here every pixel that is on a car, it will give the same color code. And every pixel that belongs to a person, maybe child or adult, it will give him the same color code. In the sky, all of them, they have the same color code. And what is in the right side here is just zooming in this region. Okay, but so the goal here for now is to group the pixels that belong to the same class to give them the same color code. That is the task that we are going to solve. And we call this one semantic segmentation. But we can define another task that is called instance segmentation. And now we will see some examples of it. So it is not just about medical image analysis or robot perception, but it can be present in many other tasks as well. So inshallah, today in this presentation, I will give you some examples from the dentistry data. Okay. So what is the image segmentation? It can be formulated as a classification problem of the pixels. So it is a classification on the pixel level with semantic labels. So the semantic labels refer to the semantic classes that you are trying to find in the image. And we call this problem up to this point, we call it semantic segmentation task. But we can add more partitioning on the pixels that belong to the same class and separate them into two different multiple instances. For example, here we have car number 1 and the car number 2, and both of them are colored with the same color. So, but for instance segmentation, we give them different colors. So what is different between instance segmentation and semantic segmentation? The countable objects will be separated from each other. The countable objects will be separated from each other. They will not be the same mask. They will have different color codes. So what is semantic segmentation? Again, it performs pixel level labeling with a set of object categories, for example, human, car, tree, sky, for all image pixels. Thus, it is generally a harder undertaking than image classification. Why? Because the image classification is giving a label for the whole image, but semantic segmentation is giving a label for every pixel. So this example from a self-driving environment, it has cars, the environment has people, has traffic signs, and so on. So this is what is meant by semantic segmentation. What is instance segmentation? Yes.
Professor Torki, may I ask a question for the previous slide, please?
Mm-hmm.
Yes. So in the previous slide, yes, in the previous slide where the cars are seen, if it is a classification task, the question for the picture will be, does this picture contain cars or not? And based on this particular image, it will be yes, right? So this is a classification task.
Yes. This is a classification. We give a label for the whole image. But you might have multiple labels. So you can ask one question for people, one question for cars, one question for road, one question for sky, and one question for something that is not here, maybe bikes. There is no bike here, so you ask also the same question. And
if it is a semantic segmentation task, it will give the all cars the same blue color, right?
Every pixel that is on a car will be colored blue.
Okay, if it is an instance segmentation, it will give each car a separate color?
Yes.
So
every countable object. For example, people are countable. Trees are not countable. Cars are countable. Sky is not countable.
Okay. I understand. Thank you.
So the countable objects will give different things. So for example, here, each person will have different mask. and it will have different color code. So we are grouping the pixels that belong to the same person into the same mask. What is meant by mask? Mask means there is a color code unified for this person. That's what I mean. Okay, is it clear now? So put them in the same image, because this is the contrast will make things clearer. Here we have an image with 4 persons. So if it is a semantic segmentation task, then you will color every person of them as a blue mask. So we'll give all of them. This is only one color code for the whole class. One color code for the 4 persons. Here we have different color code for every person. Person 1 will have color code light blue, dark blue, green, yellow. So we have different color codes, which means we have 4 masks. But on the left, we have 1 mask. Okay, so let us see one example for semantic segmentation and innocent segmentation on some 3D CBCT data. So, for example, you have a 3D volume coming from a CBCT scanner, and then you would like to find the ion or find the bulb. Okay, what is on the left? This is the voxels that belongs. These are the voxels that belong to the ion. Okay. Okay. In the middle, we have these are the voxels that are colored here with the same color for the bulb. So you might try to learn a model to do semantic segmentation on a single class. You just want to find the ion. And also in the middle, in this one, you would like also again to do semantic segmentation on a single class. So this single class will have one color code, and you are just looking for this class. And here in this one, you don't look for the ion. You just look for one class, which is the bulb. And also on the left, you just look for one class, which is the ion. Okay. And then you can do another problem, which is you are doing semantic segmentation, but on multiple classes. So we have class for the ion, which is colored as red, and we have another class for the bulb, which is colored with yellow here. So depending on your task, you would like to either find the nerve only. Maybe in some studies you just need to the nerve. In other studies you need the bulb and you don't need the nerve. Maybe in other studies you need both of them. Okay, and the last one on the right is instant segmentation. We are actually this bulb and is coming from one tooth different from this one. So you give it different segmentation mask, which means you have different color code for every bulb or for every tooth. So what is the best configuration for your problem? You have to decide which modality you are going to use. Here we decided you would like to work on 3D CBCTs, and you would like to know the anatomical structures inside this as a 3D volume. Here on the left, we are just looking for the nerve. In the left middle, we are just looking for the bulb. In the right middle, we are looking for the bulb and for the ion. And on the right side, we would like not only finding them, but actually we would like to find the bulb for each tooth. Okay, so according to your definition of your problem, you want to work on semantic segmentation with one class, or semantic segmentation with multiple classes, or even you would like to work on innocent segmentation. Okay, this is one example. Another example may be coming from panorama X-ray. Here we would like also to do semantic segmentation. In this example, we would like to segment the pixels that belong to the ancestors, which are colored with the blue color. and canines with the cyan, and premolars with green, and molars with yellow. Okay. So also you would maybe some other researcher doesn't want to work on semantic segmentation for 4 classes. Maybe you would like to find every tooth and give them one label. So all of them may be having same color coding, and in this case it will revert to semantic segmentation with one clause. So I think these examples can give you the feeling what is the segmentation doing for the panorama X-ray or for the CBC. It can do different things depending on the problem definition that you would like to solve. So, but the task from the dentist, the researcher, is to define the problem and define the ground truth annotation for the training data. So this is the task that you need to do. The labeling, maybe I can give you some hint about how to do the labeling, but I'm not preparing presentation for this part because this is not my job. It is the job for the dental research. But I can give you some hints at the end, inshallah, at the end of the presentation.
Professor, we have a question in the chat from Nilzia. She's asking, can periapical segmentation be done using periapical X-ray?
Of course, but what is the input? You have a preapical X-ray, and what is the task from the dental researcher is to provide annotations for the lesions that they are looking for in the preapical X-ray. Okay.
Okay. And another question
you
also
have to
like
prepare the data. You have to prepare the data.
Yeah. Another question, can segmentation be used in low resources with low quality radiographs?
Actually, most of the machine learning or deep learning algorithms, they are doing down sampling for the data, because processing one large volume of many voxels or even these images is very time consuming for the training, and we can get good results with small images as 512 times 512. So for example, if your image may be coming from a camera that is 2000 by 2000, most of the time we don't use the very high resolution. Most of the time we use models that use maybe 500 by 500 or even 800 by 800, no larger than this. So in this sense, I know from my expertise that the original images resolution is much higher than that. So it is okay to reduce the image quality, but not too far. Not like, don't make it 100 pixels by 100 pixels. This will be a disaster. But 500 by 500 is good enough for many deep learning algorithms.
Okay,
So
I think for most, yes, for most maybe dentists or for many dentists, the exact resolution level like 500 by 500 or so may not be known. But maybe this is like a general question about the quality of the radiographs.
Let me give you, 500 by 500, the image is less than 1 mega on the hard disk.
Okay, okay.
Which is very, very compressed. Usually you have one image coming from your mobile phone as 14 mega. And this mobile is 14 megapixels, so you can get the sense.
Yes, yes. Thank you.
I have worked with panorama X-rays, and the default sizes was like 1,600 times 1,200. This is the default size for the panorama X-ray that I downloaded from public datasets. And I didn't work on this size. The researchers worked on very much smaller size, 500 by 500.
Okay.
This is one example. Also, the problem is not in the deployment. Once your model is done for the training, to ship the model on the device, you might not need very much computation. You need the computation for the training, not for the testing, not for the deployment, not for shipping for people in their clinics or in the research centers. But the problem is to train the model. It's not to evaluate the model. It's not to deploy the model. Okay. Actually, many models can be deployed on CPUs, not GPUs even. So, but the main, the problem is in the training, not in the deployment, most of the time.
Okay, thank you.
Okay, so in order to work on your problem, you have to understand what kind of data you're working with: 2D X-rays, 3D CBTs, intraoral RGBs. Maybe you have additional modalities. You might be working on many modalities, not just one. Even if you are going to do semantic segmentation on, for example, this one, you can also use the panorama X-ray as an additional modality, and it might give you some feature fusion from the 3D and the 2D to find the masks that you would like to do. So this is another, but it is a little bit sophisticated. So let us now start with uni model problem that you have one modality, 3 CBCTs, for example, or 20 panoramas, maybe. Also, you need to define your success metrics. I will give you some brief about what are the metrics that is used for semantic segmentation and evaluation. And then to decide if your model is doing a good job or not. So the most important metrics for evaluation, they are the dice coefficient, the IOU, intersection over union, and the HD95. What is the output from semantic segmentation is masks. So you are giving the model, assuming this is the ground truth result. Your model will produce some masks. They might be correct or might not be correct. So if the overlap between the predicted masks and the ground truth mask is relatively high, then this is good segmentation. And this is the metric that we use to compute the overlapping. We have two metrics. The first one is the IOU, which is the intersection over the union. And we have also the dice, which is 2 times true positive divided by false positive plus 2 true positive plus false negative. So these two metrics are usually the two metrics that are used for evaluation for the overlap metric. But we also might need to work on the quality of the boundary. So the boundary of the mask that you are computing and the boundary of the ground truth mask. And here we use HD95. HD95, it means the Hausdorff distance. The Hausdorff distance is computed between 2 point sets. We have point set number 1 and point set number 2. And the Hausdorff distance computes the closest point from the second set to the first set, and the closest point from the first set to the second set. And then they compute the average between these two metrics, two numbers. But this is Hausdorff distance 100%. Due to some noise, you don't want to compute the distance between the two nearest points from the two sets. You would like to allow some robustness by computing 95 percentile. So you are not computing the closest point. The closest point, it means the 100% percentile. But HD95, it computes the distance between 2 point sets. The first point set is coming from the boundary of the ground truth mask. The second point set is coming from the boundary of the predicted mask. And you compute the closest, you are computing the full set of distances between every point in the first set to the second set, and also you are doing the reverse. And you sort these distances and select the 95% percentile. This will give you the HD95. Okay. So this is for accurate boundary prediction, and it is very important in many applications. You're not just doing overlap without actual boundary alignment. So you'd like to have both. You have overlap and boundary alignment as well. Okay, so the dice and IOU, the higher they are better, but for HD95, the lower is better. Okay, any question in this valuation metric?
Yes, yes, please. Yes, please, Professor. So for maybe in the previous slide where the teeth are colored, okay. Yes, this one. The HD95 would be how, for example, tooth maybe 12 and 11 are not overlapping, something like this?
No.
Oh.
Okay, let me illustrate here. I'm not sure if I have this pointer option. Maybe
for the other metrics, maybe let's begin with this. Like the intersection over union and the dice index is how well, how well the reality. Okay, okay.
I will give you something. So this, for example, I produced this mask for this tooth. Okay.
Mask is the color of the you gave it a color. Yes.
I draw a boundary now on the predicted mask for the tooth number 28, and I'm not looking at any other thing now. Okay, I'm just looking at 28, right?
Okay, okay.
So if the overlap is great, then you think that this segmentation is good. So let me tell you where is the overlap. The overlap is this colored red ones, right?
Yes.
Yes, so this is the overlap, right?
Okay.
Okay, so I compute the number of pixels in the overlapped area. I count them now. They are counting. Every pixel that is overlapping will be counted. Okay, let me give another color. Another color. How to get another color? I don't remember.
It is. I think what you're trying to demonstrate is that some of the yellow of the original 228 is not covered, and the red circle is also including. Yes, yes. This is not included.
Yeah.
And yes, so it includes something which is not 228 and misses part of 228.
Yes. So the ones that I correctly captured, they are called the true positives. So the overlapped region is called the true positive. Okay, because I predicted correctly and I predicted them as positive class, right?
Yes, yes, yes.
Yeah, and the outer region here is called false positive. False positive. I assume they are positive, but they are not positive. Okay. And this one on the left are called false negative. I said they are negative, but I am not telling. And my telling is false. So that is what is meant by false negative. So it's false negative.
Yes.
So what is the intersection over union? It is the true positive, okay, divided by the whole area, which is the true positive plus false positive plus false negative. And that is the intersection over union. Okay, the dice coefficient is some other calculation, but it is also overlapping the score. Okay, I think now the overlapping scores are easy to understand. Let us take another tooth and then give you what is meant by the Hausdorff distance. Okay. On the 48, I predicted the boundary as this one, right? Do you know, Professor Maha, how can I make the pointer with different color?
No. If any of the attendees can know this, can tell
pink
us.
color. Yes, this one.
Okay.
Okay, and this is the other boundary, right, of the other ground truth mask, right?
Okay.
So you would like to compute the overlapped area. You are doing this dice and IU. But if you'd like to compute the quality over of the boundary that you predicted, which is the red one, with the boundary which you didn't predict, which is
the blue one.
The ground truth as which is the blue one. So you compute point-to-point distance. So you find which point from this red curve, which one is closest to this one, this one. So there is a distance, very huge distance between 2 points, right? This is the closest one. And you compute this one, you find the distance here is equal to 0. You compute this one, you find the distance is 0. But between this one, which one is the closest to this one is the closest, which is too much. So you find all closest points to every point on the red curve.
Okay.
And rank them. 95% percentile, it means you are not taking the minimum or taking the maximum. You are taking 95% percentile to allow for some robustness. Because if you took the minimum, it will always give you 0. You see? So you rank the distances and get the 95%.
Yes. Okay.
So these are the two metrics: boundary quality or overlapping quality. Okay.
Yes. Thank you.
Other metrics, they are usually used for classification. Some papers are reporting accuracy for semantic segmentation, but I find this very odd because it is very usual to get very high numbers for accuracy. Accuracy means your label is matching the ground truth label. But for example, in this image, we have too many background class, right? So for example, your model might make mistakes in these foreground classes, but it is very rare to make mistakes on the background classes, or the error in the background classes will be little. But if your background class is very good, for example, you are doing very good job with the background class, the total pixel accuracy will be high, but this is not good metric for semantic segmentation. You know what I mean? For example, if you would like to detect 4 instances in an image, 4 instances give you like maybe 200 pixels, and you have more than 1 million pixels. So if you are computing the accuracy, if you miss the 200 pixels, you still get like 90% accuracy. So it's not making any sense. That's why we don't use the classification metrics, which are precision, recall, or accuracy in these problems. That's why we prefer usually to use the segmentation metrics, which are DICE, IEU, and HDM5. Because this is very elusive and it is much better suited for classification metrics. Okay. And if you can observe them here, okay. Usually we have four numbers to compute: true positives, false positives, true negative, false negative. The accuracy, for example, is that you are adding the true negative to the numerator and adding the true negative to the denominator. So, for example, if the true positive, false positive, and false negative are negligible compared to the true negative, this number will be almost close to the 1. So that's why it is not preferable to use accuracy metrics on the pixel level segmentation. Okay. These metrics are not suited exactly for the segmentation task, but it is good to understand what is the mean absolute error and also specificity and sensitivity. We can, I think most of the dental researchers are working with sensitivity and specificity in many other problems. So it is not hard to understand. We don't use these metrics on semantic segmentation because they are not very relevant. The true positive rate, which is the sensitivity, we use it here in the IOU, but we don't need to find it separately. It's not very likely to be useful. Maybe the false positive rate is very important because the false positive rate means what on this figure? The other part that is outside the correct mask that you are predicting. So, for example, if you are looking for a small lesion and the segmentation mask is very large, it means maybe the opinion of the dentist might be biased because the AI is telling you the segmentation mask is like this one, and then you cannot depend on the AI model comfortably if the false positive rate is high, because you cannot trust it in this case. So it is very important to reduce the false positive rate. One way to understand the quality of your algorithm is to compute this AUC, because it gives you the relation between the false positive rate and true positive rates for 1 minus specificity and insistent. But we don't usually use them in reporting as a main metric. Our main metrics are usually the DICE, IOU, and the Hausdorff distance. Okay. So which paradigm I'm going to use in my segmentation task? And actually, I'm going to elaborate on this because I understand how difficult it is to find labeled data. If you have enough labeled data, then directly go to the supervised approaches. Okay. If you don't have enough training data, maybe you can make use of some semi-supervised or self-supervised approaches that requires only a subset of labeled data, not the whole set. So, for example, you have 500 CBCTs. If you can find the 500 corresponding annotations for them, then go for supervised learning. If you don't have these 500 annotations, but you can obtain maybe 12, 40, 50, this few number of annotations, then you can still make use of the whole data set, but with fewer subset, with a smaller subset of labeled data. I will give you now some illustration of this. So what is, why would you select semi-supervised over supervised? As I told you here, if you have some rare labels or you have some problems that prevent you from finding a good model, maybe some resources are not good enough to run a very sophisticated model, then you might think of simpler model. So these are some reasons that you might need to change the learning paradigms that you are going to use. Let us start with one that is easy to see, which is the supervised, fully supervised one. Okay. I might come back to this slide later. I think this is not in the correct order. Let us now move forward and understand what is the supervised learning architectures that are commonly used. So on the left side, you have an image, and on the right side, you have an output map, which refers to color codes for every pixel. Okay. So this is very general image that you would like to find the masks for the floor with one color, for I don't know what is this, maybe it is a door, I'm not sure, maybe it's door or whatever. Okay, so you are giving different color codes for every pixel here, depending on some predefined task. So how is this related to our semantic segmentation tasks in dentistry? Here you have a panorama X-ray, and here you have the masks that you are trying to find. So as you can see on the output map, we need to predict the masks. We need to predict the masks to give every pixel of this width and height image some color code or some label, call it label. So most of the supervised learning approaches are using something called encoder, decoder, architecture. The idea of encoder-decoder architecture is very simple. You process the image using some neural network, some feature extraction approach, whatever it is, and then you summarize what you have seen here in something called the latent representation. And this is called the encoder step. So you understand what is in this image and write them here in this block. Okay. Whatever the technique, I don't actually care now about the technique. And the decoder part starts from this latent representation and tries to use some neural architecture or some other approach to do the decoding. And the decoding part is responsible of producing this output map or the labels for every pixel. So learning this encoder-decoder architecture is done via some neural network algorithm, backpropagation algorithm, whatever. You are feeding the algorithm with pairs, image and label. And we call the label for this image ground truth. And through the learning, the architecture here that is called the encoder-decoder will learn whenever they see this image how to produce this correct output. This is what is called encoder-decoder architecture. Okay. The most commonly used encoder-decoder architecture in medical imaging in general and also in dentistry is called UNet. The UNet is encoder-decoder, but the encoder is being done on multiple steps. First, they process the whole image. Then they downscale the image and process a smaller version of it. Then they do more downscaling, more downscaling, more downscaling until they reach the primitive features, which is the latent representation that I was mentioning on the top. Okay. And then the decoder steps are going exactly the reverse order from this latent representation to a larger representation, to a larger representation, to a larger representation, to a larger representation, to be equal to the same size of the input, but they are predicting the output segmentation map. Very similar to this idea, and why they call it UNet? Because it takes the shape of the letter U. Okay. So they are doing the encoder on multiple scales, and they are doing the decoder on multiple scales. This one is called the contractor pass, and this is called the expander pass. They have two passes, one coming here and the other one coming here. Okay. Similarly, there is some neural network is called the VNet, and this was for volumes, not for images. So the UNet was proposed for images, and VNet was proposed for volumes. But is it taking the same shape? And they call it VNet. Some newer architecture is called WNet. WNet is 2 units. It is doing what? It is doing encoder, decoder. But what is the decoded part here is not the final output. So they learn the features on a two steps. The first one, computing some intermediate representation of the same size of the input, and then for this intermediate representation, do the contractor pass and expander pass. Okay, so these are very relevant architectures, and they are very widely used in image segmentation for medical domain, especially UNet and its variants. Okay. Here is one example from one paper I co-authored with my master student. She was doing semantic segmentation on panorama X-ray, and this on the bottom here, this is the ground truth. This should be the mask that should be predicted. And on the top was the original panorama X-ray. And here we have 4 outputs because we used the 4 different techniques. They are mostly using UNet and its variants. And we can see there are some differences. Some red pixels means they are false positives, and there are some blue pixels that are false negatives. And we can see, for example, on the right part, it is giving the best results. So this one paper that I co-authored for doing batch in UNet, as you can see, it is a variant of UNet for high resolution semantic segmentation. In this paper, we found that many research just doing the down sample for the image to be able to process using the UNet, because you see the UNet standard input is 572 times 572. So if the image is larger than this, then you reduce the quality of the image and then you process it. So what we have done in this paper was to process the image in patches. We don't process the image as a whole. We keep the high resolution, but process in patches. We process many batches, but every batch will be maybe 500 by 500, and we slide the batch on the image and then accumulate the results to find the final output. Okay. Another work, but on 3D volumes. So this one was fully supervised learning approach. So the learning paradigm here was supervised learning, and we had 1,600 panorama X-rays coming from public datasets, publicly available datasets. Okay. So also another work, but was done on CBCT volumes. CBCT volumes, here we have 3D volumes, and we worked on segmentation for the bulb and for the IM. And this paper was published at MyCai 2024. My co-authors was Mahmoud Gamal from Alexandria University and Dr. Marwa Baraka from Alexandria University. Mahmoud was my master student at Computer and System Engineering Department, and our collaborator was with Dr. Marwa Baraka from Faculty of Dentistry at Alexandria University. So it is also something similar to the UNet and VNet on 3D data, but we added something called attention post-bed UNet. Position padding. It means position padding because the volume is very large to process. So we computed batches of size 80 times 80 times 80, and we process these batches during this attention post-bed UNet. But the problem, if you are processing these batches without ordering, then you might mistake the final output. So we encoded the positional embedding inside the network, and we added it here to be able to recover the volume output size correctly. Okay, and here we worked on tooth theory dataset. Tooth theory dataset is very well known for the. It has multiple, many volumes, and 500 volumes or more, something like this. And it has segmentation for the IM. And actually, we manually labeled the bulb because at that time, 2024, there was no publicly available data set that has bulb annotation. And Dr. Marwa Baraka, she led that contribution here. And we produced this PulpI 3D data set that is doing the 3D pulp annotation on the tooth theory data set. Okay. What about semi-supervised framework? This is another work that was done by some researcher in Knight's lab at Alexandria University. And the work was done on some set that is called C-tooth dataset. C-tooth dataset, it has just 24 labeled scans only. And the dataset itself, it has 300 volumes. And the goal for this task was to generate the hard tooth structure I'm sorry, the full tooth segmentation, not bulb, just the tooth. So the problem was the very few number of labeled volumes, and to do the solution, we have done this in iterations, and we have these loops. So, for example, we start with the volumes with the annotated data, and then we create some model, and this model now learned a little bit from the annotated data how to produce the output volumes. So if we have unlabeled scan, we have the scan but without labels, we pass it on our model and we generate pseudo labels. The pseudo labels, as you can see, are very noisy. They are getting some red tooth on unusual places. So what we do is to filter out these bad predictions using voxel level entropy. The entropy measures something called the homogeneity, and we do this post-processing module. Then we can get from this that still there are some mistakes and the annotations are not very good. So the post-processed pseudo labels will, for example, I said we have 300 unlabeled scans. So the ones that will pass the confidence criteria, maybe at the first iteration will just be 50 or 20 scans. We will add these 20 scans to the training data and learn a better model. And this model will give us some pseudo labels, and these labels we will keep the confident ones of them. And now we have 150 good. We are not very sure about the quality of them because we don't need the actual quality for these ones. We need the validation set to be better, but we, as you can see, there are some noise, and still the next step will be better than the first step. And we have done this until we finished, this one. So, for example, this was the ground truth. The first iteration was like this one. The second iteration was better. Third iteration was better, and fourth iteration was the last model result. The baseline is some other model that used only the 24 annotated masks without doing this our approach using voxel entropy. Actually, we did also some iteration on it, but without the voxel entropy criteria. So we can see that our contribution was twofold. The first thing is to do the active learning module, which is self or semi-supervised approach. And second thing was contributed here also was voxel entropy post-processing module that keeps the good scans and adds them to the training data. Okay. And this was published with Al-Badri, who was my internship at Knight's Lab. Mahmoud Gamal also contributed, and Dr. Marwa Baraka was my collaborator as well in this research, and it was published on ICMLA 2025. Okay, so do you have any questions about this kind of works?
Any questions? Any questions from the audience? I think it is what it shows is that very complicated techniques do exist to deal with different scenarios and adapt to data availability and the context and the resources. I'm not sure that people who are non-AI experts will sort of like digest all this, but at least the impression I get is that there are solutions to problems. So any questions? Okay, maybe we can proceed to the last part of the presentation. Professor Torki, please.
Okay. For the last part, it is a little bit more math. So I'm not very sure if I would like to go into more details in this part, but I will give you the story in one figure. Okay, just this one. Okay, what is the intuition for learning? The intuition for learning is this. You would like to find something that makes your model do correct predictions. Okay, that is the story. I would like to do correct predictions. That's it. Okay. To do the correct predictions, you have to find the best model. So what is done in learning is to search for the best model. That's it. This is the goal. How to do this goal? How to get to this goal? You first start with initial random model that is very bad. Just give the model the random weights, random initialization. And you do the loop this way. You apply the models that you initialized on the training data. But if you apply the model that is randomly initialized on the training data, you will not obtain good predictions. You will always get bad predictions. Once you get the bad predictions, compute the difference between the correct prediction and the predicted output, the ground truth, I mean, the difference between the ground truth and your predicted output. If there is much difference, it means the loss will be high. So the way we write the model and learn is using the calculus, something called the derivative. You know, the derivative, that's some topic that we calculus and so on. So you do something about the derivatives and compute how should I update my initial model. So we start with random weights. After you compute the loss, you do the back propagation, the derivatives and the calculus, and update the weights. And do the loop once again. Do the forward pass, compute the predictions, compute the loss, compute the derivatives, and update the weights, and so on. At every time, once you calculate the loss, you might check your evaluation metrics, IOU, DICE, or whatever, on the validation set. And once you find your validation set metrics are settling at a good results for you, you stop this loop and finish. Okay. So this is the intuition for the learning, and that is what is going to be happening. If you need more details, then I can tell you about this here. So the very simple task of the model learning is to estimate from the input X and the output Y, what are the weights, the theta, the weights that we are trying to find. So given this function f on this input with these weights, I should obtain the correct y. But if I get some prediction that is not equal to the y, then I need to update this theta. And I iterate between these two steps, compute predicted y, and update the theta, compute the predicted y, and update the theta until I find good enough results. So the core steps after you define your model, what is the function f? And here, what is the function f in our problems? The function f is this one. Maybe unet, maybe vnet, maybe wnet, maybe other architecture. So this is the function that is called f function. What is the x? X is the input image. What is the y? Y is the predicted output. What is learned in theta? They are the parameters that controls how the function operates on these inputs. So the goal is to adjust the theta, the parameters, to minimize the error between the prediction and true outputs. The forward pass calculated predictions, the loss calculation measures the difference between predictions and the true labels. And the backward pass computed gradients or derivatives to update the parameters using the back propagation. The next slide may be offensive. You have the x as an input, and you have every arrow of this one is called weight. We have W, 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 W. And the architecture is called the feed-forward neural network. And the goal is to estimate Y1 and Y2. So what is the function f? Computes this from this X computes Y1 hat and Y2 hat, the predictions. If these predictions are close to Y1 and Y2, then we are happy. If they are not close, we have high loss, then every arrow, it has a weight, should be updated. How we compute this update? Using back propagation algorithm. So the back propagation updates the weights according to the derivatives, as you can see. We can visually see the effect of the back propagation. As, for example, this is a function on higher dimensional data. You start with some loss that is high, and you would like to find the minimum loss here. So what are you going to do? Is going to adjacent to the surface, and that is what is called the derivative. So you go with a direction that is adjacent to the surface, and then it will lead you to the minimum here. But it doesn't give you directly here. You must go through the surface, and that is what is called the weight update using the back propagation. Okay, the optimizers, I don't need actually to go more deeper in this part, but they are the basic algorithm is SGD, and they are modifications to make the results faster, to find the minimum faster. Okay. The loss function that is used in the training at some task, like our task, the segmentation, we usually use the dice score as part of the loss function. So we might combine cross entropy with dice score. But what is meant here, the dice score is very important loss to work with in the semantic segmentation or instant segmentation. Okay, and these are the most common losses: cross entropy, MSE, L1 focal loss, or combined between dice score, dice cross entropy, and Jacquard focal loss. So I will put this slide one more time. You start with initial weights, you do the forward pass, calculate the loss. If your evaluation metrics are good enough, stop and you are fine. If not, you are doing back propagation, update the weights, and go in this cycle until you are happy with your metrics. Okay, that's it for today.
Thank you.
I think if you understand the problem, your problem carefully, then you can decide if semantic segmentation or instant segmentation is better for it. And for the calculations and this kind of learning, actually, I don't think it is very important for you to understand every part of it, but you have to understand something like big idea what is going to happen, like this one slide. Yeah.
Thank you, Professor Torki, for the comprehensive presentation. Any questions, please, from the audience? Any questions? Any questions and thoughts, comments? I have actually some like non-detailed questions. Okay, the first is related to logistics. We have your permission to record the presentation and post it on our YouTube channel. Is it also possible to share the PowerPoints or?
Yes,
What?
No problem.
Thank you. The second is for the use of the computer vision in dentistry. Most of the input data that we saw were related to different imaging, like radiographs in their different kinds, like CBCTs, MRIs, X-rays, and stuff like this. These, by definition, happen in clinics and may be restricting the use of AI to people who can actually visit the dentist and make use of this service. Is there a room in the use of computer vision for the broader public health aspects of dentistry, like using data that is not related to X-rays and radiographs and stuff like this? What's your thoughts on this, Professor?
Actually, we can work on any other modality. We don't have to work on radiographs. For example, mobile images for for the teeth of the children, maybe we can use mobile. We don't have to go for radiographs. We can develop our models on this kind of data, which is actually present in every mobile. You can use your mobile. So I don't find this is blocking. The most important thing is to annotate.
It seems that based on the options that you raised, like supervised and unsupervised learning, that annotation is like a considerable problem, so to the extent that there are computing techniques to address this. Is this correct?
I'm sorry, someone interrupted me. Please, can you repeat this one?
I mean that the annotation is an issue that takes time and resources because of this,
And
because
also,
yes, and training and
must be
calibration.
trained and calibrated with the criteria.
Yes, so and maybe this is why there are computing options to use, like unsupervised learning to get rid over this problem, something like this. Is this correct?
I prefer semi-supervised learning. Actually, without any labels, it's not going to work well.
Yes.
Yeah.
Yes.
Few
Yes. There has to be
labels.
some labeling.
Yeah.
Yes.
Even if even few might make things better. Yeah.
Yes, exactly. Okay, so if there are no questions from the audience, we'd like to extend our thanks to Professor Marwan Torki at Alexandria University. Thanks for the comprehensive presentation and for sharing the resources. And we look forward to continued collaboration in this respect. Thank you very much. And have a great evening, all audience. And we meet in a new AFRONE webinar. Thank you. Thank you.
Thank you.
Salam.
Thanks.
Thank you so much.
Thank you. Bye.